What's up, folks? So today I'm going to, now I'm going to code the model portion. I'm going to pick up right where I left off, the training loop, and I'm going to code the model portion of Rectified Flow. I'm going to code the backbone. So this Unet pixel space, right now it's just, I just added a linear layer so that the training loop works. But now I'm going to add Unet and I'm going to inject the time step embedding into Unet, okay? So basically I'm gonna have ResNet blocks that downsample Unet. So I'm gonna have Unet downsampling and then a Unet decoder upsampling and passing skip connections. So just like we've done in previous videos. So I'm gonna move through this quickly because I've done this already. The only difference is I'm going to inject the time step embedding, okay? Okay, let's get started. So Unet pixel space. So these are the modules we're gonna have. We're gonna have class upsample, we're gonna have upsample, downsample, ResNet block. And I think that's actually it. So the ResNet block, what we're going to pass in, the XT and T, and essentially what we're gonna do, so it's our typical ResNet block, right? It's stacked convolutions, right? So we're gonna have, right, we're gonna do, so we're gonna normalize, we're gonna activate, and then we're gonna convolve. Sometimes we normalize, convolve, activate. I'm gonna take this route, I think, for this model. I think either one would give us very similar results. But once we do that, right, we're gonna get this hidden, this latent, and we're gonna have some kind of time projection that knows the dimensions, that knows how to project it so that it can match H. And we're going to project, it's going to be a time embedding. It's not T. We've already changed T into an actual embedding. So we're going to pass the embedding in here, and then we're going to project the embedding to the dimensional space that we want. And then we are going to, we're going to drop this out. And then we are going to, let's restart this timer. We're going to drop it out, and then we are going to normalize, convolve, activate, normalize, Yeah. No. Convolve, activate, normalize. Right. We're gonna stack it, then the dropout usually comes at the end of all these operations. That's a good convention to remember. Typically, when you have these modules, you usually drop it out at the end, and we need the skip connection, right? So then we need to activate H plus skip XT. Yeah. This is our ResNet block. This is the main difference, is that we're passing in. Well, in the videos I've coded before, we're convolving the activations as opposed to passing convolutions into the activations, right? And then we're projecting the time step embedding, and we're adding it onto that latent before we send it through the next convolution. Yeah, this is what I want. This is what we want. Okay. And then our upsample is going to be our unit is going to call upsampling and downsampling, right? The encoder is going to downsample, the decoder is going to upsample. So how about we just fill these in now? So let's do downsample first. Yeah. So downsample is going to have, so we're going to do strided convolution for downsampling, okay? The last unit I did, I downsampled using max pool, okay? This time I'm going to downsample using conv2d. Okay, right. Channels, in channels and out channels are going to be the same. Kernel is going to be 3. Stride is going to be 2. Padding 1. Okay. Maybe I'll make it more explicit. Okay. Actually, that's yeah, I'm going to use a convolution here too. So I'll copy that there. And the forward is just going to return self.conv x. Yes, that's our downsample. Right, so this stride is going to divide the height and width by 2. Upsample is going to have a conv, and we'll just call it up, which is going to be upsample scale factor 2, right? It's the inverse of the downsample, and the mode is going to be nearest neighbor, because it's a well documented. It's your go-to for upsampling. And then we're going to return self dot, and then wait, we can't forget to do this. self dot, we're going to upsample, no, we're going to convolve. Yes, we're going to convolve the upsample. And then we need to make sure stride is not 2, because then that would just downsample again. So stride is going to be 1 and padding is 1, so it's same padding. Okay. That's downsample and upsample. Let's do ResnetBlock. Actually, you know what? Let's do Unet pixel space. So we know our ResnetBlock is just stacked convolutions, right? Right. So this is why knowing fundamentals is so important. It's like, you know what the purpose of all these things are. Like, why do we, what does ResnetBlock introduce? You can think about the name, you can forget about the name Resnet, okay? Forget about it, right? People are like, oh, why do I want to learn Resnet? You're not learning Resnet, you're learning the techniques that Resnet has put forth. What are they? Stacked convolutional layers. What is a Resnet block? Stacked convolutional layers to increase the receptive field without increasing the number of parameters, and skip connections, right? That's what a Resnet block is, you know? So now you have this technique, and you can use these, you can deploy these techniques whenever you need them, right? Like, you know that the stride of 2 is a downsample, right? So you know if you want to deploy downsampling, you can use a convolutional layer with stride of 2. And you know what inductive bias is. You know that, right? We can make the choice on the fly. We can say, I want to make a smaller model, right? A model that uses a smaller data set, okay? I know if I want results quickly on a smaller data set, I'm probably gonna want to use something with inductive bias, right? I know that sliding dot products give us translation equivariance, right? That's our inductive bias, and amongst a few other things, right? This is why first principles and fundamentals are so important. Don't let anybody tell you, oh, you don't need to know ResNet blocks or Unet or all those things. Yes, you do. You need to know all these techniques. If you really want to build, if you want to be a scientist, if you want to be an applied researcher, right? If you want to be just a run-of-the-mill engineer that just stacks, agents together, that's fine. That's not a big deal. If that's what you like, that's great. That's not what I like. I like knowing things from the ground up, right? So this is why you need to practice these techniques. It's really important. Okay, rant over. So, okay, let's go to Unet, all right? We know, so we're gonna have this, first of all, we have this time embedding, right? And so we need to, so I have this time module, right? And I did the video on sinusoidal time embeddings, right? Sinusoidal embeddings, but we want to make a time embedding that passes a sinusoidal embedding to an MLP. Okay, that's going to be our time step embedding. And so to do that, I'm going to make this module right? I'm going to use the same constructor, and then I guess the only difference is I'm going to have an MLP, actually no, MLP, right, okay. So this is going to be, it's going to have a sinusoidal embedding module. We're going to pass in dim, and it's going to have an MLP, just a sequential layer. It's going to have and the activation is going to be SIL-U. Boom. This is our time embedding, right? Oh. It's going to take in a scalar, and it's going to turn it into, first it's gonna turn it into a time embedding using sinusoidal, using sine and cosine, right? So now it's no longer gonna be just shape B, it's gonna be shape B time dim, right? And then we're gonna say, we're gonna pass that to an MLP. So now what we have is what we have is what we have is we have the advantages of the sinusoidal embeddings, right? We have this measurement system that we create on the fly, tailored to a number of dimensions, dim, right? That's continuous, and it's an efficient measurement system. And then we can add the flexibility. We can pass that into an MLP and add the flexibility of having learnable parameters on top of that, right? So research has shown that this is one of the best ways to do time embeddings and position embeddings. Outside of rotary embeddings, which we don't need for this because we don't need the benefits of rotary embeddings right now, right? Which I'll do a video covering that once I do a model that uses rotary embeddings because they're really cool. So, okay. Now back to Unet. So, okay, we have our time embedding. Boom. Okay, so the first thing we're going to do is we're going to transform this. Let's place a debugger. Actually, let's use this main method. We're going to say in channel C, time dim is going to be 128. Oh, we'll just say 30. We'll just say 16. P dropout. Let's say it's none for now. Okay. Our model, and then we're going to say model torch dot ones or torch dot rand C B C H W input out dot shape. Okay. Oh. All right. This should actually run. So let's just run it really quickly. I'm saying, oh, forgetting T input T is torch dot rand shape time dim. Shape, no, sorry, it's not shape time dim. Time dim is the shape of the time embedding. That's what we pass to the constructor. This is just going to be the shape of the batch. So we're sampling values between 0 and 1 from uniformly. Okay. Okay. Oh. Okay. This. Okay. Okay, this works. Creates a time embedding appropriately, but let's place the debugger here, okay? time embedding should be of shape B, and then 16. So debug tm.shape. Yep, 416. Okay, cool. So now let's keep coding. So what do we want? We want, okay, we have our time embedding. Now we want to create the encoder. Okay, so we're going to do, what do I want to call this? So let's call this yep. Yes. So let's see. ResnetBlock in channel, out channel. We're gonna do 128. So we're gonna the channels are gonna be 128, 256, 512, 1024, and then we're gonna do 1024 middle. It's gonna be 1024 channels to 1024 channels. Then we're gonna have the decoder. I wish I could reverse those easily. Boom, that's what we're gonna do. Okay, so this is, okay. Time dim. P dropout. All right. Okay. $256, 512, 1024. I think these are pretty standard number of channels, but this is good. I think this is pretty good for the data sets we're going to be using. I mean, 1024 features. It's plenty for faces. It's plenty for Flickr 30K. Maybe once I move up to the Lion data set, like a million, once I really start doing well, once I move up to that data set, I won't be using Unet anymore. I'll be using a diffusion transformer. So 1024 features should be good enough. If we need to bump it up to 2048, we can do that in the middle. Oh. Wait, channels 128. Wait, sorry, not upsample. Downsample. Okay. Now this. In forward. Oh. So Okay. Oh. Okay, so what we should get out of this is a B, C, 128, and then it downsampled to 16 by 16, okay? Okay, and then we're gonna place the debugger right here and restart it. What's it saying? Conv2D received an invalidation combination of parameters. Where? 80, line 80. Oh, line 80. Line 68. Oh, down. Interesting. It didn't even. Maybe it breaks. Okay, we're here. Boom. Let's step. Step into the. Oh, wait. Yeah, no, duh. I didn't do ResnetBlock. Okay, let's do ResnetBlock. Spin 25. So, ResnetBlock. Okay, we need conv1, norm 1. We're going to do something different for. We're going to do. Number of groups, num channels. Okay, I'm gonna make this helper function called get groups. It's gonna take in the number of channels. Eight, 4, 2, 1. Sweet. I will just call it C. If C, so we just want to make sure that the number of groups divides it out, because I've run into this channel I've run into this issue a bunch where the number of groups doesn't divide the number of channels, and it has to. So Okay, get num groups. Okay. Skip is going to be 2D. Kernel size is going to be 1, so it's just a pass through, just to make sure that the in channels equal the number of out channels. You all have seen me code this many times if you watch my channel. Skip norm conv. This is going to be three. Padding is going to be 1. Okay. And then we also need this time projection. It's gonna, we're gonna do time dim, right? So the time dimension, you need to project the time step embedding to the number of channels. Okay. Right. And then we're gonna broadcast it. Across H. Okay, and then this is going to be, out channels. This is going to be in channels. Yeah, because we're calling normalization first. Then out channels. This is out channels. Right. And then okay. Is not none else identity. Oh, there you go. Okay. I like this. I think this is good. 1. And then we're going to do I have an F? Yes, I do. I have my functional imported. Boom. I like that. This is going to be on xt self.conv 1. Look good. Now I'm projecting. So now my time step on the T embed is it's going to be B time dim. And then after I project it, it's going to be B out channels. Okay. And then self.time projection T. Now I need to, just like I did in the last video, I'm going to do B out channel and then none, none to make it 1, 1, right? And now I can broadcast that, right? You know what, how about I make it explicit? Okay. Now I can add it. Okay, so you see that. So now I'm gonna clean it up. Okay, and then we're gonna do self dot norm 2. Okay. F dot boom. Self dot boom. Self. Now we finally do skip connection. Boom. This is looking good. It's looking good. Coding neural networks is really fun. Tensor math is challenging at first. It really is. It was for me. It was challenging, just the coding. Well, the math was okay, but then the coding, the NumPy, getting the shapes properly when coding was really difficult for me. And then once you just practice a bunch, like literally how I did in my videos, then you're like, oh, this is actually a lot of fun and it's cool and it's you know, like I always say, everything is easy once you know how to do it. Okay, so takes one positional argument, but 2 were given. Oh, yeah, of course. Wait. Get num groups. Return. Interesting. Oh. Sorry. Get num groups takes one. Oh, there's no self. Right. So yep. What's the shape? It should be out channels, so it should be 4, 128, 32, 32. Yep. Yep. Now it should be 4, 128, 16, 16. Yep. Downsampled well. And got weight of shape 3 and input shape 4, 128, 16, 16. got weight of shape 3. Expected weight to be a vector of size equal to the number of channels in the input. Channels in the input are 128. I was probably complaining about the convolution. Oh, yeah. Oh, yeah, yep. In channels 128, 256, 512. Okay. Let's put this here. Actually, this is just run. If it runs, we know we're good. Yep, we're good. Okay, so 256, 8. Actually, let's do this. I'm gonna stop this video. It's been 40 minutes already. I did the encoder. So we're gonna do this. Okay, so we're gonna do 3 and 4. 3, 4. Wait, oh, what happened? 2, 3, 4. 2, 3, 4. Now, okay, look, this is too small already. And then it's 2 and 2. That's too small. Okay, so we're gonna have to remove some of these downsamples. Let's remove the first 2. Okay, so we're gonna remove this, and this. All right. And then we're gonna downsample. We'll just keep the numbers the same. Okay. Keep the numbers the same. So that we're going to keep downsample 3 with encoder 3. We're going to delete those 2. Actually, let's just, so it's explicit so you guys see. And so that here it's going to be 32, 32, 16, 16. Oh. 32, 32, 16, 16, 8, 8. Actually, let's do, yeah. 32, 32, wait. 16, 16, 8, 8. And then I want the middle. We'll downsample it one more time. Actually, you know what? I'm going to downsample. I'm going to downsample like this. I'm going to downsample like this. Yeah. I'm going to downsample. Yeah, because it's a convolutional downsample. It's a strided convolution. So this works. I'm going to downsample 1, 2, 3, 4, and then I'm going to have a mid block. So let's do this. Let's do downsample 2. So this is coming from the previous layer. Yeah. Downsample 3, down 4, H. Mid is going to be another ResnetBlock, right? So 32, 32, and then this brings it to 16. Comes out of this, it's 16. This brings it to 8. Comes out of this, it's 8. This brings it to 4. 128, 256, 512, 1024. And I'm going to keep it 1024 in the middle and 4, 4. Yes. 4 is still a small image, but it's okay for the data that we're using. In the middle, it's going to be ResnetBlock 1024, 1024. Remove this. This should work. Yep, works. Let's see. Out.shape should be 4, 1024, 4 and 4. Oh yeah, it is. Boom. Okay. All right. Next video, I will do the decoder. And then I'll do inference. Yeah. Thanks for watching.